This is a trip to the moon, calculus of parametric and polar equations, part 4, confirming Kepler's second law of planetary motion. Okay, so now we made it to part 4 of the series. We're studying the calculus of parametric and polar equations as applied to a trip to the moon, and because we're using Kerbal Space Program to illustrate these principles, actually we're taking a trip to the Mun, the nearest moon to Kerbin, the home planet of the Kerbals. As I calculated the mission to the Mun in part 2 of this series, I had originally planned a transfer orbit with a semi-major axis of A equal to 6350 kilometers and an eccentricity of E equal 0.8898. However, executing the required translunar injection burn in part 3 to enter the transfer orbit, because the engine burn was not executed precisely as planned, we entered an orbit with a semi-major axis of A equal to 6,471 kilometers with an eccentricity of 0.89183. Very close to the original planned orbit, but not precisely the same. So these values were really close to my original planned orbit, so I proceeded to fly along that trajectory. So now in this part of the series, we'll look back at the orbit we have followed so far and confirm Kepler's second law of planetary motion. Kepler's second law of planetary motion states, as an object orbits around a primary body, equal amounts of area are swept out in equal amounts of time. For example, in the figure here, the areas shaded in blue would be equal if the time periods from one endpoint to another are equal. That is, as a rocket, satellite, moon, or planet travels along an elliptical path, it does move faster when it's closer to the primary body and slower as it travels further away, and as a result, the time it takes to trace out sectors of equal area are the same. It's traveling faster from this point here to there, and so this amount of time that it takes to trace out this sector of area, it's the same. Even though it's moving slower here, this amount of area would equal that amount of area. At the left is another illustration of Kepler's second law. For example, in exactly 1 month's time, imagine that this took 1 month to travel this interval from this point to that point. In exactly 1 month's time, the Earth will sweep out equal amounts of area within its orbit around the Sun. So if this is a month, this would be another month interval from this point to this point, and that area A. This region is A, same as that area, and this would be, it would take a month to travel this interval right here. It's going much slower, and the area in this sector would be the same as the areas in these other two sectors. So all these areas are equal, and these intervals of time are the same. I should probably mention that, of course, the picture isn't really drawn to scale, and on this scale, the orbit of the Earth around the Sun would look much more circular. You wouldn't really be able to detect the eccentricity of the orbit, be essentially a circle. And so it's pretty nearly traveling the same speed at any interval during the entire orbit. So perhaps a better example would have been to say, imagine a comet coming in close to the Sun and then going out further away from the Sun. So this applies to any object in an elliptical orbit. So that means it's true for the Earth, true for satellites going around the Earth, it's true for the Earth going around the Sun, all the planets going around the Sun, or any satellite orbiting the Earth, for the moon orbiting the Earth, for a rocket orbiting around the planet Kerbin, or in a transfer orbit from the planet Kerbin to the Mun, or for a rocket traveling from the Earth to the Moon. These principles all apply. This second law of planetary motion applies in all of those orbits because they're all elliptical orbits. So in this part of the series, we'll confirm Kepler's second law of planetary motion in Kerbal Space Program, and we'll use the websites Desmos and GeoGebra to help with that investigation. So in general, the area of a polar sector defined by some function r equal to f of theta is given by this formula below, here. So we're looking at the area of some region like this shaded region here that's bound by two different angles in polar form and some curve that's traced out by some function r equal to f of theta. So to find that area, you integrate from the angle A to the angle B the function 1/2 times the function squared, the function that defines that boundary in polar form. And the integration is with respect to theta. And also for the area to truly represent area, we would require that the angle A is positive between 0 and 2 pi, and B is between 0 and 2 pi, and that A is less than B, so that we don't have any situations where we're reversing the order or the boundaries are kind of overlapping each other in a rotation. So we require the angle between 0 and 360 or 0 and 2 pi and the A value less than the B value. And of course, if we're talking about a elliptical orbit in polar form, then the function that we're integrating is this function here, where A is the semi-major axis and E is the eccentricity, and the angle theta is what we call the true anomaly. It's the angle that drawn from the focus of the ellipse at the center of the primary body out to the object that's orbiting. Well, let me see if I have it. This is the picture, right? This is the angle theta that I'm trying to integrate some interval from one value of theta to another along that orbit. So the angle theta actually starts at a line drawn from the focus to the periapsis, and theta is drawn up to some point P, some radial vector that determines that point P, I guess I should say. So given that the path in polar form, the elliptical path, an elliptical orbit in polar form is given by this function, traces out this path, something like this curve here, areas with an elliptical orbit can be computed by an integration from some alpha to beta 1/2 times the r value, the radial position of that object in orbit, right? So this is the r, right? R is this function a 1 minus e squared over 1 plus e cos theta right there, and you square it. Now what I've done here is I recognize, of course, the 1/2 as a constant, but in the integration, so is a and e. These are constants. So I'll factor all of those out because it'll make the integration easier to evaluate without those factors in the way. So for a given ellipse with a fixed semi-major axis and fixed eccentricity that don't change in the integration and don't change during the orbit, we'll only need to compute just this integral here. Therefore, we'll confirm for a given elliptical orbit with a fixed semi-major axis A and eccentricity E that this integral here produces the same value for different intervals alpha to beta. We'll confirm that a same amount of time, same interval of time, same length of time from some alpha to beta, it'll be the same area for different intervals. Right? So for example, looking at the first half of that transfer orbit that we're on from Kerbin to the Mun, I decided to investigate the following two intervals. From point 1 to point 2 along the path, when the true anomaly was 100 degrees, that's here, and at 120 when it's here, I'll look at that interval and I'll confirm that that area that's swept out from point 1 to point 2 is during the same amount of time, I'll have the same amount of area as when we travel from point 3 to point 4. And that'll be when the true anomaly goes from 130, it'll have to be about 136.48. We'll not be able to get that one exact because we're doing a numerical integration and we don't have precise agreement on the eccentricity. And well, also, you'll just see that since we're doing a numerical integration here, we can make this as accurate as we want by just carrying more and more decimal places. And so at some point, we'll just say that's close enough. So we can find that it's very nearly, very accurately measured to about 136.48 degrees when this time interval is the same as the time interval here. You see that it's traveling slower. It takes in a certain amount of time, in that fixed amount of time, it doesn't get as far when it's traveling slower, and we'll confirm that this area matches that area there. We will be confirming that the shaded areas in this diagram are equal. We can check the time in Kerbal Space Program at the endpoints of each of these intervals, measured by the true anomaly, and then use Desmos to calculate the areas of the corresponding regions. So first, here I am in GeoGebra, and I've had the computer sketch out for me the elliptical orbit, the transfer orbit from Kerbin. Here's the planet Kerbin over out to the Mun, and I've labeled those 4 points, 2 points on each interval that I'll be checking to confirm Kepler's law. So you see the angle is down here, about 73 right now. That's the true anomaly, measured from periapsis when we're closest to the planet up to this radial vector. You can see my eccentricity is pretty close to what I have running in the simulation. Here I have 0.89183, but then it goes on a little bit more, few more decimal places, so they're not precisely the same, both in the game and here in GeoGebra, but I think it'll be close enough to be useful. And so what we're going to do is we'll look at from the point when the true anomaly is 100, you see, going to have to say approximately 100 degrees right there. So from that point to this point, how long does that take to when we get to 120, somewhere right around there. So we'll look at that time period and we'll measure that area. And then I'll start another interval from point 3 when the true anomaly is 130 degrees, and I'll track to when the time interval is the same going from point 3 to point 4 as it was from point 1 to point 2. Of course, we know it's slowing down, so we're going to see a little bit shorter distance in how far it actually travels, but we will be able to confirm that the area that's swept out between point 3 and point 4 in this ellipse, this area in here, that should be the same. So you see this orbit now is going a little bit past, because also we're going to have to sort of adjust so that once we get into the Mun's sphere of influence, we want to be able to actually get into a circuit or orbit around the Mun so that we don't just crash into it or miss it. So, all right. Now remember, of course, this is the basic formula for finding areas of polar sectors, and the actual curve that we're using is an elliptical curve in polar form, which is this function. And so we're doing this integration 1/2 times the r value, but because a and e are not changing as we integrate from one point on that interval to another, I'm going to factor out the a squared and the 1 minus e squared. Of course, a squared because this is getting squared in the numerator. So all these factors here in the numerator, they're all constant in the integration. I factor them out. So really the integration that you're going to see is this 1 over 1 plus e cos theta, where e is the eccentricity. And so I've got that set up in Desmos to actually do the integration on those two time intervals. So now in Desmos, I've actually set up the function 1 over 1 plus the eccentricity times the cosine of the angle squared. But just because it was convenient here in Desmos, instead of using theta, I'll use x as the angle. And I couldn't use e in Desmos as the eccentricity because it sort of expected e to be the constant 2.17. So I'll set k to be the eccentricity, and I'll put it at 0.89183 to match very closely with what I observed in the game in Kerbal Space Program. So I'm using that eccentricity for k. And what I'll do is I'll label this point A, f at A, and B, f at B. So what I could do is I can now trace out different intervals here and actually measure what that area is. So this is from an angle of 100 to 120, and these are the values of the function 1.4 and 3.38. Yeah, actually one thing that might be kind of nice to see is like if you go to 90, you get 1. Why would you get 1? Because if you put 90 in for the angle, the cosine of 90 is 0, so you have eccentricity times 0, so just 1 over 1, so you get a value of 1 at 90. But we're actually going to start this interval at 100, where the value of the function is 1.4. Just this function. It's not the actual r value, it's just the part that I need to check for the area. So I label those 2 points and have it shade this interval right here, and I get this point C and D that I'll do the same. And so I can now, looks like this is actually 120.5. I want to go at 120. There it is. And then this actually is computing that area, which is coming out really, really close right there at those values. So here I'm getting more area for this region G. I wanted that to be 136, about 136.478, and I saw that match pretty closely, 43.1 roughly for both of those areas. I can zoom out just to give you a sense of what that curve looks like, and with that pretty high eccentricity, yeah, the curve is pretty steep there, but I could drop this back, and then it's just a different eccentricity, and it's easier to see the entire curve. But of course now the areas aren't going to necessarily match. We're pretty close there. So yeah, we could now I could go and investigate other time intervals and look for equal areas. So, for example, from 100 to 120 degrees true anomaly, it's the same when you go from about 205 to 210. So that 15 degrees increase in the true anomaly will take the same amount of time as it does for this 20 degree increase in the true anomaly. Well, I got to be careful when I say that. They would take the same amount of time if you were on an elliptical orbit with an eccentricity of 0.66, which is not, so we wouldn't be able to confirm that specific relationship on this particular elliptical orbit. We had a different elliptical orbit. It was 0.89183, and so, yeah, so now they would totally not take the same amount of time. And have to make the time interval much. I mean, yeah, to make the time interval the same. Well, as it's traveling here from 205 to 207, it'll take about the same amount of time as it took to travel from 100 to 120, right? So that's about a 2-degree change, and that's not even really quite accurate. Let me try that a little bit more. So there we go. That's pretty close. Right, so that's just a sliver right there of area. So at that interval, when you're going from 205 to 206.65 true anomaly, after orbiting around the apoapsis, it's still going really slow. And so the time it takes to get from 205 to 206.65 is roughly the same as the amount of time it takes to get from 100 to 120 true anomaly on this particular highly elliptical orbit, right? Because it slows down dramatically as it gets out there near the apoapsis. That would be assuming that there was no, the Mun wasn't there, and so we actually really just kept traveling right along this path. Here's my true anomaly right there, that 185 degrees. So as it goes from what we had about 200, or actually it was 205 to 206. So that little bit right there, from 205 to 206, it's the same as traveling from 100 to 120. The area right here from 100 to 120, that area is the same as this area from 205 to 206. And that takes the same amount of time. So it's traveling much slower at this point in the orbit. So back in Desmos, when I'm integrating this function, let me bring these two intervals back to the time intervals that I want. So I went from 130, starting at 130, until about 136.5, somewhere around there, and I want to confirm that these areas are the same. But actually that's with an eccentricity that was on the orbit that we had, 0.89183 roughly. I'll make it that. So that's this curve, right? So finding the areas here. Now these should be the same. That's what I'm checking here. And yeah, so it was actually more like 478 to yeah, this is, and this had to be 100. Okay. So yeah, to one decimal, actually to two decimal places. Well, one decimal place if you round each of these. If you round each of these to one decimal place, those areas are the same. And yeah, I can confirm that in the game that it takes the same amount of time to go from 100 degrees to 120 as it does to go from 130 to 136. So that's an increase of 16 degrees, a little more than 16 degrees in the true anomaly. It takes the same amount of time as it did 20 degrees because it's traveling slower as we get further away. The time it takes to get from this point P1 to P2, that's about 10 minutes, 10 seconds, and this is going to be 10 minutes, 10 seconds because it's slowing down. So by confirming that from 100 to 120 degrees takes the same amount of time from 130 to 136.48 roughly, we'll be able to confirm Kepler's laws, Kepler's second law of planetary motion. It's because we've confirmed that these areas are the same by integrating under this function. Just to finish off on that little error that I had written in there, of course when I'm squaring the numerator I get a squared and 1 minus e squared all squared, and didn't matter actually because we're going to use the same ellipse on this path. So A doesn't change and the E doesn't change. And so really to calculate the area and to confirm it's the same, this quantity doesn't change. All I really need to do is check the areas for just this integration. So this doesn't really represent the actual area of the sector of the ellipse, but it's the part that's actually going to change in the integration from one bound alpha to some other bound beta. So I only really need to calculate this part. So the fact that I forgot that square as I was writing it out and use this, it didn't matter. But yeah, there really was supposed to be a square right there. Okay, so now let's check it in the game. So here we are looking at our crew on their way to the Mun, as seen from the data collected in the tracking station on Kerbin. We can see in the menu on the left of the screen a lot of the flight data that an engineer at the Kerbal Space Center would be tracking, such as position and speed and the true anomaly. We'll take a moment here, like looking over the shoulder of that engineer, to confirm Kepler's second law. We'll be waiting until that angle of true anomaly reaches 100 degrees. And then we'll wait until it reaches 120 degrees, and we'll want to record the time between those 2 points. We can see mission elapsed time, MET, also up in the top left of the screen. They're measured in years, days, hours, minutes, and seconds. Okay, right about there, at mission elapsed time 49 minutes 33 seconds, we observe true anomaly at 100 degrees. Now we are going to wait till 120 degrees true anomaly and record the elapsed time. So there it is, at 59 minutes 43 seconds, true anomaly 120 degrees. Thus we have an elapsed time between the 2 points of 10 minutes 10 seconds. Now we wait until the true anomaly reaches 130 degrees and record the time to start that second interval. That was it. At 1 hour, 9 minutes, 45 seconds, true anomaly at 130 degrees. So now we're just waiting another 10 minutes, 10 seconds on this interval, and based on Kepler's second law, the true anomaly will then be 136.48 degrees. Therefore, we are expecting at 1 hour 19 minutes 55 seconds to see a true anomaly of 136.48 degrees. And there it is. We have confirmed. At 130 degrees, true anomaly, mission elapsed time was 1 hour, 9 minutes, 45 seconds. And at 136.48 degrees, true anomaly, mission elapsed time is 1 hour, 19 minutes, 55 seconds. And that is a total elapsed time of 10 minutes, 10 seconds for that particular change in the true anomaly. So that's it. Kerbal Space Program very accurately models Kepler's second law of planetary motion. We could call this Kepler's space program. Anyway, I think Kepler would have loved to learn about the Kerbal system. Now, I'll admit, I'm splicing together two recordings of the same trip so I can capture everything I want in this video. So mysteriously, our mission elapsed time has suddenly jumped ahead a couple of hours as we approach the Mun. Again, that's only because I'm using video from two recordings of the same trip. Probably this trip I must have left a little later, or I made a few more orbits around Kerbin before entering into that transfer orbit. Either way, in both recordings, I needed to deal with something pretty obvious if you know even a little bit about this game. In fact, if you do know a little bit about this game, you might know more than me. I am really just a KSP beginner. But that isn't stopping me. This is a lot of fun, and it's a lot of fun to use this game to illustrate some ideas that I teach in the calculus class. So that's really what this is all about. So if you're playing this game, you'll know that I didn't need to make a big deal about the phase angle in part 3 that I was determining the right time to initiate that translunar injection burn. I was talking about all that to make connections to some basic concepts of trigonometry, and everything I said there was mathematically correct. However, I neglected two important points. First, we don't want to fly our crew directly into the Mun, and second, as we approach the Mun, the gravity of the Mun will affect our orbit. In the game, you don't have to determine the phase angle actually for the trip to the Mun. You would for other planets, but if you're going to the Mun, you just eyeball it. And you probably want to set a trajectory when you set that maneuver node at a point where you'll actually get a periapsis with the Mun. And I didn't pay attention to those obvious concerns in part 3, and well, actually, just like in reality, as a real crew, like the Apollo crew, we can continue to monitor the trajectory and perform course corrections as needed along the way. So that's what I'll do now. As I approach the Mun, I recognize I need a course correction to intercept the Mun with a periapsis for the orbit. decide I don't want to crash into the Mun and I don't want to miss it, and I'm not sure which one of those would have happened, but neither is good for the purpose of this video. So the goal for the next part of the series is to orbit the Mun and do some science there. So in this part here, I'm just trying to correct my trajectory to actually get a periapsis so that I can actually get into an orbit around the Mun. So I'm not really doing the math here, I'm just sort of playing the game, but intuitively what I see is that I'm kind of overshooting where the Moon's going to be. Going to be on sort of the other side of its orbit. And then right at that point we enter into the Moon's sphere of influence, and so we now have a different trajectory. And I want to get the periapsis. Basically, I want to get into a circular orbit now. Right now I have a parabolic orbit, but I want to get an elliptical orbit first and then a circular orbit around the Mun. So I need to follow this path, and so somewhere near the periapsis I'll set a maneuver where basically, yeah, I'm going to slow it down. Slow down. So I'm passing the Mun and then kind of slowing down and getting into an elliptical orbit there. I can adjust a little bit further, make it closer to a circular orbit. So yeah, we've passed the Mun a little bit, but then we'll slow down on our parabolic trajectory there so that we can enter into an elliptical orbit. So we can speed up time in the game so we don't have to wait that whole entire period until we get to that maneuver node. So you'll see as we approach that maneuver node there, I'm going to fire the rockets retrograde. That is sort of opposite the direction we're traveling. That's going to slow us down, and that'll change the orbit from parabolic into elliptical right here. So that executes the maneuver. Now we're in elliptical orbit. So next, in part 5, I thought there would be two interesting things that we could do. Once we're in an elliptical orbit about the Mun, first we can check our flight data for altitude and speed, use that data to compute the mass of the Mun. I imagine that is like the crew in Star Trek approaching a new planet or moon that they've just discovered. With altitude and speed, we could use some physics and algebra to determine the mass of the moon that we're now orbiting. And then second, we could check that value that we just computed for the mass of the Mun and confirm orbital speed and that calculation using the equations that I had introduced to determine orbital speed for a circular orbit, as I had introduced that back in part 1 of this series. So I think that's it for this part of the series. I hope it's been interesting and fun. And hope it's been helpful in learning some calculus.